I'll start week 6 of this course, and in this week we will discuss the commonly used crystallographic notations for point groups and space groups. As I had said earlier, there are two notations that are common. One is called the Schoenflies symbols and the other is called the Hermann-Mauguin conventions. So, we will discuss both of these, but it is the Hermann-Mauguin that is more commonly used in crystallography. So, before we go to the actual notations, let me tell you about how you get 32 classes, 32 crystal classes. So, in the first lecture we will talk about crystal classes. So, week 6 lecture 1 will be on crystal classes based on symmetry. So, now what are crystal classes? These are the crystallographic point groups, and these are actually very similar to molecular point groups, the point groups of molecules. In fact, they are identical to point groups of molecules. These crystallographic point groups are referred to as crystal classes. Now, you may have seen, you may have learnt about molecular point groups in a course on group theory in chemistry, okay. And so crystallographic point groups are basically shapes of crystals, okay. And so now not all molecular point groups are valid crystallographic point groups, okay, because only those shapes that satisfy the space filling requirement are valid crystallographic point groups, okay. So what I mean to say is that the number of crystallographic point groups is much smaller than the number of molecular point groups. Now there is another point which I am not going to talk too much about, but basically these crystallographic point groups reflect the outer shape of crystals, and this has to do with a rather subtle theorem regarding the shapes of crystals. So if you take a finite size crystallite, okay, then the shape of that crystal will be reflected in the, it will actually reflect the shape of the unit cell, okay. And so the outer shapes of crystals will actually carry information about the point group of the unit cell. And historically this was a very powerful idea in the development of crystals, because many of these crystals were actually, the early crystals that were discovered were minerals, and while if you look at shapes of these minerals, mineral samples, okay, you will often find that they have exquisite crystalline shapes, okay. So there are fairly large crystals and these are fairly exquisitely shaped, okay. And so you can look up shapes of crystals of especially minerals, okay. And if you take any one well formed crystal piece, okay, the shape of that crystal will be reflected in the crystallographic point group. But in any case, we will not talk too much about the outer shapes of crystals here. So let us get back to the crystal system based on symmetry. We already saw that there are 7 crystal systems: a triclinic, monoclinic, trigonal, hexagonal, orthorhombic, tetragonal and cubic, and this is based on symmetry. Triclinic has no essential symmetry, whereas monoclinic has one 2-fold axis or mirror plane, trigonal has one 3-fold axis, hexagonal has a 6-fold axis, orthorhombic, tetragonal, cubic, okay. Now let's now look at these in terms of let's see how these lead to various crystal classes. So let's first look at the most unsymmetric crystals, okay. So if you look at the triclinic system, that has the least symmetry, and if you take actually there is no essential requirement of symmetry. Okay. So, if the only symmetry operation that is present is an identity which is basically means doing nothing. So, if the only symmetry operation that is present is the identity operation, okay, that means the crystal has no essential symmetry. Of course, it is a crystal, so the translational symmetry of the crystal is there, but there is no other symmetry in the crystal. Then that crystal class is referred to as the PDL crystal class. Okay. Now, the other possibility in the triclinic crystal system is where you have an inversion axis. So, you have only one symmetry operation, and that is an inversion. So, crystals that have an inversion symmetry and nothing else, their unit cells will be triclinic and they will fall in the pinacoidal crystal class. Okay. So, these are the most unsymmetric, where you do not have any symmetry. In the monoclinic, you have to have at least a two-fold axis of rotation or a mirror plane. Okay. And so, there are three possibilities, where if you only have a two-fold axis of rotation in your crystal, then it is sphenoidal, okay, and it will fall in the monoclinic crystal system. It will be sphenoidal. It is called, the crystal class is referred to as sphenoidal. If you have a mirror, just one mirror, okay, then the crystal class is referred to as domatic. Now, if you have a two-fold axis of rotation and a mirror perpendicular to the axis of rotation, okay, then automatically that implies that you have an inversion center in the crystal, and the crystals that only have these symmetries are referred to as prismatic. Okay. So, the crystal class is called as prismatic. Okay. And again there are several examples for each of these. Okay. I am not going to go into the actual examples. Okay. Then but these show that monoclinic there are three possible crystal classes. In triclinic there are only two crystal classes. Okay. So, we see that triclinic there are only two crystal classes. Whereas in monoclinic there are three crystal classes. What about orthorhombic? Now, orthorhombic means it should have three two-fold axis or mirror. Okay. Now, it can have three two-fold axis, or it can have two mirrors and a two-fold axis, or it can have three two-fold axis with perpendicular mirrors, and each of these falls in a different class. Okay. So, again there are three crystal classes. These are referred to as rhombic disphenoidal, rhombic pyramidal, and rhombic dipyramidal. Okay. So, now you can see that these groups have only one two-fold axis, okay, of rotation, if at all. Okay. Some of these have no axis of rotation, okay, like the domatic or the PDL and pinacoidal. Okay. And everything has at least one two-fold axis. Okay. Now, let's go to more symmetric crystal classes. So, now we look at the tetragonal. So, in the tetragonal there are 8 classes, okay, and these 8 classes are tetragonal pyramidal, tetragonal disphenoidal, and so on. I won't go through all the names. Okay. But let us see the operations. So, a tetragonal means it has to have a four-fold axis of rotation. So, if it has only a four-fold axis of rotation, then you call it tetragonal pyramidal. If it has a four-fold roto inversion axis, then you call it tetragonal disphenoidal. If it has a four-fold axis of rotation and a mirror perpendicular to it, then you call it tetragonal dipyramidal. If it has a if it has a 4-fold axis and 2 2-fold axis of rotation, then you call it tetragonal trapezohedral. Now, if it has tetragonal axis and 4 mirror planes, okay. Now, I am writing only 2 mirror planes, we will see soon why we write only 2, okay. But basically if it has a 4-fold axis of rotation and mirror planes and 4 mirror planes, then you call it tetragonal pyramidal or ditetragonal pyramidal. If it has a 4-fold roto inversion axis, a 2-fold axis of rotation and a mirror plane, then you refer to it as tetragonal scalenohedral. And if it has a 4-fold axis with perpendicular mirror and 2-fold axis with perpendicular mirrors, okay. So, actually there is a total of 4 2-fold axis with perpendicular mirrors, okay, and there are and then there is one mirror perpendicular to the 4-fold axis. So, actually there are 4 2-fold axis of rotation and 1 4-fold axis of rotation and total of 5 mirrors, okay. Then you call it a ditetragonal dipyramidal, and this is the tetragonal structure with the highest symmetry. So, the tetragonal class crystal class with the highest symmetry is this ditetragonal dipyramidal, okay. Next, let us look at the trigonal hexagonal systems, okay. We will look at both of them together, okay, both the trigonal and hexagonal, we will look at them together, okay. So, now there are a total of 12 classes, and I am not going to list all of them in detail or describe all the operations in each one of them, but basically trigonal systems are characterized by having a 3-fold axis of rotation. Hexagonal is characterized by having a 6-fold axis of rotation, okay. Now, if you just have a 3-fold axis of rotation, then it is referred to as trigonal pyramidal. If you have a 3-fold roto inversion axis, then you refer to it as rhombohedral, and so on. If you have a 3-fold and a 2-fold axis, then it is trigonal trapezohedral, and these names of the various crystal classes are based on the shapes of the crystals, on the outer shapes of the crystals, okay. So, these are all solid objects, okay. These are geometric objects that have these are shapes of geometric objects. If you have a 3-fold axis and a mirror, then it is referred to as ditrigonal pyramidal. So, if you have just a 3-fold axis, there is trigonal, it is called trigonal pyramidal. If you have a 3-fold axis with a mirror, it is referred to as a ditrigonal pyramidal, okay. So, similarly you can see if you just have a 6-fold axis, then it is referred to as hexagonal scalenohedral, okay. If you have a 6-fold roto inversion axis, then it is hexagonal pyramidal, and so on. You can go through the entire list of symmetries. Now, the dihexagonal dipyramidal has a 6-fold axis with a perpendicular mirror and 2-fold axis with perpendicular mirrors, okay. So, here there are 12 classes in the trigonal and hexagonal systems, okay, and these are in some sense highly symmetric, okay. But the highest symmetry, the crystal class with the highest symmetry, the crystal system with the highest symmetry is the cubic system, and the cubic system gives the most symmetric classes. There are 5 crystal classes in the cubic systems, okay, and these have names, okay. So, in crystal class terminology, they have slightly different names than the point group names, okay. But in any case, I am just listing these for completeness, okay. So, if you have so remember, a cubic system is characterized by 4 3-fold axis of rotation, okay. So, in every case you have to have 4 3-fold axis of rotation. Now, if you have in addition to this, if you have 3 2-fold axis, then you refer to the system as tetroroidal. If you have 4 3-fold axis, okay, and 3 to 2 axis and 3 mirrors, then you refer to it as diploidal. Okay. Notice that the moment you have 4 3-fold axis, okay, you automatically end up with 3 2-fold axis. Okay. So, now this is another property of this. If you have 4 3-fold axis, okay, then again just based on symmetry, you have to have at least 3 2-fold axis. Okay. So, you cannot have just 4 3-fold axis, okay, because the 4 3-fold axis will intersect at some point, and usually if you take a product of 2 of them, then you will get a 2-fold axis. Okay. Now, this has a 2-fold axis with a perpendicular mirror, and in addition to the 4 3-fold axis. Okay. Now notice on the left, I am not writing all the symmetry elements, I am just writing this 2 by m3, okay, and again this will become clear. Okay. So, it turns out that only this 2-fold axis with a perpendicular mirror and a 3-fold axis that is sufficient. Okay. You will automatically, because of this 3-fold axis and this mirror, you will generate a total of 3 mirrors, and actually there are 3 2-fold axis that are generated again because of this 3 axis. Okay. In this case, it is a 3 bar axis as opposed to a 3 axis. This is referred to as diploidal. Then you could have 3 4-fold axis, 4 3-fold axis, and 6 2-fold axis. This is called gyroidal. Then you could have, so notice here there are no mirrors. Okay. So, in this gyroidal system there are no mirrors, there are only but there is 4-fold axis, 3-fold axis and 2-fold axis, but there are no mirrors. Okay. And again this 3 4-fold axis, 4 3-fold axis, and 6 2-fold axis, these numbers 3 4 6 are fairly standard. Okay. Now, in the case of hexatetrahedral, you have the 3 4-fold axis, but now they are 4 bar roto inversion axis. You still have the 4 3-fold axis, and instead of having the 6 C2 axis or the 2-fold axis that you had in the case of gyroidal, you have 6 mirrors. Okay. And this is referred to as hexatetrahedral. Okay. And finally, this is the axis that we have seen before. Okay. So, you have a 4-fold axis and a perpendicular mirror, and then you have 3-fold roto inversion axis, and you have a 2-fold axis and a perpendicular mirror. Okay. This is a 48 operations that you saw in the case of cubics of the face centered cube and the body centered cube. Okay. This is referred to as hexaoctahedral. Okay. And this is the highest symmetry that you can get. This is in some sense the most symmetric crystal class. Okay. So, with this we complete the discussion of the 32 crystal classes, and I just want to make a couple of points. Okay. I do not expect you to remember the names of all these 32 crystal classes. However, I do expect that you remember that the cubic crystal has 5 classes, and you should know some important crystal classes like the hexaoctahedral or the gyroidal and so on. Okay. Similarly, I would expect that you know that the trigonal hexagonal crystal class, trigonal hexagonal systems have a total of 12 classes, and that similarly the tetragonal has 8 classes, and the triclinic has 2, the monoclinic and orthorhombic have 3. So some general information I expect you to know. Similarly, I would expect that at least for the triclinic, monoclinic and the orthorhombic, you should know what are the various possibilities of the crystal classes. Okay. So, for example, triclinic can have only an inversion or nothing, monoclinic can have a 2-fold axis or a mirror or both, and so on. Okay. So some basic information I expect you to remember. However, I do not expect you to remember the 8 classes in the tetragonal. Okay. You should know that a tetragonal system has this 4-fold axis of rotation. Okay. But I do not expect you to know all these 8 classes. Similarly, I do not expect you to know the 12 classes of the trigonal hexagonal systems, but I would expect you to know the 5 classes of the cubic systems. Okay. So I would expect you to know that these are the 5 possibilities and that these are the 5 crystal classes. So I will conclude this first lecture of week 6 here. Okay. Now, in this lecture I have tried to show how the 32 crystal classes can be derived based on symmetries, and I have used some part of the crystallographic notation, okay, that we will discuss in more detail in the next in the remaining part of this week. Thank you.